Hello, everyone. I'm gonna be reading the operating systems book again. I completed the first section. There's like a virtualization section, a concurrency section, and then another section. I forgot what it was, but I finished like the first half of the first section. The next chapter is about address spaces, and that's what I'll be reading next. Just waiting for everything to load. I think I can change to full screen. Yeah. I will only be reading one chapter this stream. I want to keep the stream small because I have something else to do. Hold on a second. Okay, I'm just testing how well the Excalibur Draw works because the last time it did not work so well. I think it's either the browser or either the fact that I'm using a virtual machine, so it's getting really slow. Yeah, it's really slow. I need to remove this. Otherwise, on my in my Windows browser, it works fine. Okay, let's read the dialogue first. So, are we done with virtualization? No. No? No reason to get so excited. Hey, no reason to get so excited. I was just asking a question. Students are supposed to do that, right? Well, professors do always say that, but really they mean this. Ask questions if they're good questions and you have actually put a little thought into them. But Joda takes the wind out of my sails. Mission accomplished. In any case, we are not nearly done with virtualization. Rather, you have just seen how to virtualize the CPU. But really, there is a big monster waiting in the closet: memory. Virtualizing memory is complicated and requires us to understand many more intricate details about how the hardware and OS interact. That sounds cool. Why is it so hard? Well, there are a lot of details, but you have to keep them straight in your head to really develop a mental model of what is going on. You'll start simple with very basic techniques like base bounds and slowly add complexity to tackle new challenges, including fun topics like TLBs and multi level page tables. Eventually, we will be able to describe the workings of a fully functioning model virtual memory manager. Need any tips of for the poor student? Inundated with all of this information and generally sleep deprived, or they sleep deprived that is easy sleep more. For understanding virtual memory, start with this: every address generated by a user program is a virtual address. Okay, the OS is just providing an illusion to each process, specifically it that it has its own large and private memory. With some hardware help, the OS will turn these pretend virtual addresses into real physical addresses and thus be able to locate the desired information. Okay, think I can remember that. Every address from a user program is virtual. Every address from a user program is virtual. What are you mumbling about or nothing? Anyway, but this why does the OS want to provide the solution anyway? Again, mostly ease of use. The OS will give each program the view that it owns a large contiguous address space to put its code and data into. Thus, as a programmer, you will never have to worry about things like where should I store this variable, because the virtual address space of the program is large and has lots of room for that sort of things. Life for a programmer becomes much more tricky if you have to worry about fitting all of your code data into a small crowded memory. Why else? Well, isolation and protection are big deals too. We don't want one errant program to be able to read or worse overwrite some other program's memory, do we? Probably not, unless it's a program written by someone you don't like. I think we need to add a class on morals and ethics. Maybe we should. Okay, address space and then zoom in. In the early days, building computer systems was easy. Why you ask? Because users didn't expect much. In those, it is those users with their expectations of ease of use, high performance, reliability, etc. From the perspective of memory, early machines didn't provide much of abstraction to users. Basically, the physical memory of of the machine looks something like what we see in Figure 13.1. Figure 13.1. Operating system, code, data, etc. Current program, code, data, etc. The OS once was a set of routines, a library really that sat in memory. Starting at physical address 0 in this example, and there would be one running program that currently sat in physical memory at physical address 64 and used the rest of memory. There were a few illusions here. The user didn't expect much from the OS. Life was sure easy for OS developers in those days. Was there only one program? Or did all the programs use the code over here? Okay, they said there would be one running program that currently sat in physical memory. Okay, so the OS would decide which program to run, I'm guessing. After a time, because machines were expensive, people began to share machines more effectively. Thus, the era of multi-programming was born, in which multiple processes was ready to run at a given time, and the OS would switch between them. For example, when one decided to perform an I/O, doing so increased the effective utilization of the CPU. Thus, increases in efficiency were particularly important in those days, where each machine cost hundreds of thousands of or even millions of dollars. Soon enough, however, people began demanding more of machines and the era of time sharing was born. Specifically, many realized the limitations of batch computing, particularly on programmers themselves, who were tired of long and hence ineffective program debug cycles. The notion of interactivity became important as many users might be concurrently using a machine, each waiting for a timely response for their currently executing task. One way to implement time sharing would be to run a process for a short while, giving it full access to all memory, then stop it, save all of its state in some kind of disk, including all of physical memory, load some other processor state, run it for a while, and thus implement some kind of crude sharing of a machine. Unfortunately, this approach has a big problem. It is way too slow, particularly as memory grows, while saving and restoring register level state. Uh, while storing and while saving and restoring register level state is relatively fast. Saving the entire contents of memory to disk is brutally non-performant. Thus, what we rather do is leave processes in memory while switching between them, allowing the OS to implement time sharing effectively. In the diagram, there are three processes A, B, and C. Or they mean here or here. So operating system, this memory is free, process C, process B, free, process A, free, free. Okay, so now it's not instead of like switching between programs. So the current program is A, then the current program is B, then the current program is C. Instead, uh, there's a small space reserved for each program, and it will switch between the CPU states instead of unloading and loading the entire content. As time sharing became more popular, you can probably guess that new demands were placed on on the operating system, in particular, allowing multiple programs to reside concurrently in memory makes protection an important issue. You don't want a process to be able to read or worse, write some other process's memory. We have to keep those pesky users in mind, and doing so requires the OS to create an easy to use abstraction of physical memory. We call this abstraction the address space, and it is the running program's view of memory in the system. And understanding this fundamental OS abstraction of memory is key to understanding how memory is virtualized. The address space of a process contains all of the memory state of the running program. For example, the code of the program have to live in memory somewhere, and thus they are in the address space. The program, while it is running, uses a stack to keep track of where it is in the function call chain, as well as to allocate local variables and pass parameters and return values to and from routines. Finally, the heap is used for dynamically allocated user managed memory, such as that you might receive from a call to malloc in C or new in an object oriented language such as C++ or Java. Of course, there are other things in there too, but for now, let us just assume those three components code, stack, and heap. In the example in figure 13.3 page 4, we have a tiny address space, only 16 kilobyte. 13.3. Okay. So all this is free. Oh, entire thing is the address space, program code, heap, free, and this is the stack. Where instructions live, the heap segment contains malloc data, dynamic data structures. It grows positively, and the stack it grows negatively. The stack segment contains local variables. Is this space fixed? Stack is fixed, right? We will often use small examples like this because it is a pain to represent 32-bit address space. And B, the math is harder. We like simple math. The program code lives at the top of the address space, starting at 0 in this example, and is packed into the first 1 kilobyte of address space. Code is static and thus easy to place in memory, so we can place it at the top of the address space. Next, we have two regions of the address space that might grow while the program runs. Those are the heap and the stack. We place them like this because each wishes to be able to grow, and by putting them at opposite ends of the address space, we can allow such growth. They just have to grow in opposite directions. The heap thus starts just after the code at 1 kilobyte and grows downwards. The stack starts at 16 and grows upwards. However, this placement of stack and heap is just convention. You can arrange the address space in a different way if you would like. We will see later when multiple threads coexist in an address space. No nice way to divide the address space like this works anymore. Of course, when we describe the address space, what we are describing is the abstraction that the OS is providing to the running program. The program really isn't in memory at physical address 0 through 1 through 16 kilobyte. Rather, it is loaded at some arbitrary physical addresses. Examine processes A, B, and C in figure 13.2. There you can see how each process is loaded into memory at different address, and hence the problem. So hence this problem. How can the OS build this abstraction of a private, potentially large address space for multiple running processes? When the OS does this, we say the OS is virtualizing memory because the running program thinks it is loaded into memory at a particular address and has potentially very large address space. The reality is quite different. When, for example, process A in figure 13.2 tries to perform a load at address 0, which we will call a virtual address, somehow the OS, in tandem with some hardware support, will have to make sure load doesn't actually go to physical address 0, but rather physical address 320 kilobyte where A is loaded. So A is loaded 320 kilobytes. So the address spaces A is using is like the relative position of the physical address, right? This is key to virtualization of memory, which underlies every modern computer system in the world. Thus, we arrive at the job of the OS in the set of nodes to virtualize memory. The OS will not only virtualize memory, though it will do so with style. To make sure the OS does so, we need some codes to guide us. We have seen these codes before. Think of the introduction, and we will see them again. One major goal of the virtualization memory system is transparency. The OS should implement virtual memory in a way that is invisible to the running program. Thus, the program shouldn't be aware of the fact that the memory is virtualized. Rather, the program behaves as if it has its own private physical memory. Behind the scenes, the OS does all the work to multiplex memory among many different jobs and hence implement the illusions. Okay. This usage of transparency is sometimes confusing. Some students think that being transparent means keeping everything out in the open, what government should be like. Here, it means the opposite, that the illusion provided by the OS should not be visible to applications. A transparent system is one that is hard to notice, not one that responds to requests as stipulated by Freedom of Information Act. Another goal of VM is efficiency. The OS should strive to make the virtualization as efficient as possible, both in terms of time and space. not making programs run much more slowly, and not using too much memory for structures needed to support virtualization. In implementing time efficient virtualization, the OS will have to rely on hardware support, including hardware features such as TLBs, which we will learn late about in due course. Finally, a third VM goal is protection. The OS should make sure to protect processes from one another. When one process performs a load, a store, or an instruction fetch, it should not be able to access or affect in any way the memory contents of another process or OS itself. Protection thus enables us to deliver the property of isolation among processes. Each process should be running in its own isolated cocoon. In the next chapter, we will focus our exploration on basic mechanisms needed to virtualize the memory, including hardware and operating system support. We'll also investigate some of the more relevant policies that you will encounter in operating systems, including how to manage free space and which pages to kick out of memory when you run low on space. Isolation is the key principle in building reliable systems. If two entities are properly isolated from one another, this implies that one can fail without affecting the other. Operating systems strive to isolate processes from each other and in this way prevent one from harming the other by using memory isolation. The OS further ensures that running programs cannot affect the operation of the underlying OS. Some modern OSs take isolation even further by veiling off pieces of the OS from other pieces of the OS. Such microkernels thus may provide greater reliability than typical monolith kernel designs. We reached okay. This chapter was much smaller than I thought. Uh, Ever write a C program that prints out a pointer? The value you see is a virtual address. Ever wonder where the code of your program is found? You can print that out too, and yes, you can print it. It is also a virtual address. In fact, any address you can see as a programmer of a user level program is a virtual address. It's only the OS through its tricky techniques of virtual memory that knows where in the physical memory of the machine these instruction and data values lie. So never forget, if you print out an address in a program, it's a virtual one, an illusion of how things are laid in memory. Only the OS knows the real truth. Here's a little program, ba.c, that prints out the location of main routine where code lives, the value of a heap allocated value written from malloc, and the locations of an integer on the stack. So main, printf main, printf malloc, then x is equal to 3, location of stack x. When run on a 64-bit Mac, we get the following output. From this, you can see the code comes first in the code comes first in the address space. Wait, so in the address space, the code comes first, then the heap, and the stack is all the way in the other end. Okay. All of these addresses are virtual and will be translated by OS and hardware in order to fetch values from their true physical locations. This chapter was much smaller than I thought. I streamed for like only 30 minutes. How long is memory up here? Okay, I need to do something. I will end the stream here. And then I think I will come back to this. Okay, I will end the stream here. It was a small stream. I just wanted to read one chapter. I will end the stream here and then, yeah, I will come back to it later. Anyways, bye.